We have a parcel. What's in the parcel? Is it a toy car? Perhaps. Is it a cat? I don't know. Hopefully not. Maybe it's some chocolate. That's what I feel like right now. But before that, let's do this problem together. So a rectangular cuboid with a square cross section. In other words, looking at it from that side, all those side lengths are the same length. The sum of the length and the perimeter of the square cross section is to be 100 centimeters. Find the maximum possible volume, right, and justify our answer. Alright, so this is a classic optimization problem in that we are trying to maximize volume, so optimize volume, and we are given a constraint to use as part of that problem. Cool. So just looking at our wonderful puzzle, we could introduce a variable. So it's not labeled, but that doesn't mean we shouldn't, right? So we could call this length x. Right, all those lengths are the same, length x. And the length, we could call that L. Alright, so we've introduced our parameters. So we could say let x be length of square cross section and L be length of parcel. Right, so we've parameterized the problem. Now we have a few things going on, right? We're trying to maximize volume. So ultimately, we're going to want an equation for volume in terms of one of our variables. But right now we have two variables, right? X and L. So firstly, I will write an equation for volume in terms of everything that we have. So volume for a cuboid would be like length times width times height. In this case, length is L, width is X, and height is also X. So it'll be Lx squared, right, for volume. Now, we're trying to maximize volume. However, we need to eliminate one of these variables. And in order to do that, we use our constraint, right? Because these two variables are constrained to each other. In this case, the perimeter, right, 4x plus L, the length, must be 100 centimeters. So 4x plus L must be 100 centimeters. So once more, the sum of the length, L, and the perimeter of the square cross section, x plus x plus x plus x, 4x, must equal 100. So we call that the constraint equation. Cool. So just so far, we've introduced x and L. We've written our equation for volume because we want to optimize or maximize volume. And we've linked length and x. So just rewriting this, for length would be 100 minus 4x. And I did that so I can substitute in 100 minus 4x into our volume equation. Right, so volume now becomes, instead of length in terms of x is 100 minus 4x, and x squared times x squared. Great, so we have our volume equation, which we can of course just expand. 100x squared minus 4x cubed. Now, to find the maximum possible volume, the easiest way would be to graph it, which unfortunately isn't enough for a calculus paper, but let's do it anyway. Now, what are we seeing here? A thick black line. That tells me my window is quite out of whack. So the constraints of the problem. This is the bit that you might not have an intuition of, because I'm looking at a solution, so I can see what to set my window to. So the max, x max, that's fine. See, the y max should be very high. Whoa, look at that. Beautiful cubic. So looking at this, if I use gsolve max, when x is 16.7, the volume is close to 9,300. So that's the point we're looking for. But of course, we need to use calculus. So we know to find a maximum that's at a turning point which has a gradient of 0. So we need to find the derivative of volume with respect to x, right, the gradient function. So 2 times 100, and then subtract 1 off the power. 3 times 4, 12, subtract 1 from the power. And we know this must equal 0 for the turning points. Right, so factorizing, common factor of x. So either x will equal 0, or 200 minus 12x equals 0. So x equals 200 over 12, which is 16.67. Alright, so we have two possible x values. Again, back to our graph. Draw. We know that this point up here is when x equals 16.7. That's a maximum. And then we know that there's a minimum when x equals 0. Right, so we found the x values of those turning points. Alright, but the question is asking us to find the maximum possible volume. So we found the x values of the turning points. So therefore volume, we use our volume equation. And in for x, we'll go 16.67. And when we compute that, we get 9,259 centimeters cubed. Now, how do we know that that's a maximum? Well, we can just check the other turning point. So that was for x equal to 16.67 centimeters. Now for x equal to 0 centimeters, the volume would be 0, right? If the x is 0, I mean we don't have a box. So that's clearly the minimum. Right? And we've shown by testing both x values for both turning points. So therefore, maximum volume when x equals 16.67 centimeters of 9,259 centimeters cubed. Alright, so let's go over these steps one more time, just briefly. So firstly, we were greeted with a parcel, and it's an optimization problem because we were looking for the maximum volume. So we had to introduce some parameters, so x and L, to find an equation for volume. Then we used our parameters in a constraint equation to find a relationship between the two, so that we could then express volume in terms of a single variable. And we did that so we could differentiate it, right? And if you got that far, that is achieved. We then set our derivative to equal 0, because we know that would correspond to the turning points, which have a maximum or minimum. And we found two solutions for x, right, because it was a quadratic equation. At that point, you could have used the quadratic formula as well. Then our last step was to find the volumes. So we checked for both x values, and it was clear that the maximum was 9,259 centimeters cubed, right? Because the other one gave us the minimum of 0 centimeters cubed. And that was sufficient justification. You could also do the sketch. So just from our calculator, right? That was the sketch, and you could label the min and the max points to clearly demonstrate that there is a maximum when x is 16.67 of 9,259, right? And 59, yeah. Right? And if you got that justification, that was excellent. Right, so you optimized your grade. Well done.